This is the 6th video in our series on a course covering ring theory and field theory. And today we want to really finish tying together the structural components of the integers and the ring of polynomials over a field. And then after this, we're going to look at some more general concepts inside of ring theory, like ideals, quotients, and so on and so forth. So let's start by recalling the definition of an irreducible polynomial. We'll need to use some stuff from previous videos as well, but we'll just use that when we get to it. So a polynomial f of x in f adjoin x is said to be irreducible if, when we factor f of x as g of x times h of x, we know that g of x or h of x is a constant polynomial. So that means that we have the degree of g of x is 0 or the degree of h of x is 0. And I really should add something right here. This isn't any polynomial. This is a non-constant polynomial. So let's get that in there. And that's because if we've got a constant polynomial, then it's a unit, unless it's the 0 polynomial. Remember, a unit is something that's invertible. And if we're talking about something being irreducible, it can't be a unit, because the definition of something being irreducible inside of a ring means that it's a non-unit. Okay, so our first goal of this video will be to prove that f adjoin x, that ring of polynomials over a field, has a unique factorization theorem that's similar to the fundamental theorem of arithmetic over the integers. So we're going to start by proving that everything can be factored into irreducibles. And then we'll show that all irreducibles are primes. And then we'll show that we get a uniqueness of factorization. Okay, so here we'll prove that every non-constant polynomial f of x and f adjoin x can be written as the product of irreducible polynomials. So we're going to do this by induction on the degree of f of x. Let's observe that if the degree of f of x is 1, and we can factor f of x as g of x times h of x, then that means that the degree of g is 1 or 0, and the degree of h is 0 or 1. And that's because we've got that sum of a degree of a product thing going on here. So the degree of f is the degree of g plus the degree of h. The only way you can achieve 1 with positive integers, I should say non-negative integers, is with 1 plus 0 or 0 plus 1. But check it out. That means that either g or h is a constant, which means f is already an irreducible. So that really takes care of the base case pretty quickly. Now let's do the induction step, starting with the induction hypothesis. So let's suppose that every polynomial of degree less than or equal to k can be factored into irreducibles, and the degree of f of x is equal to k plus 1. So this is actually going to be pretty quick. So I'm going to break this into cases, although I think you could probably write your way around needing to break it into cases. So case 1 will be f of x is irreducible. But that means that we're done already, because f of x is equal to just f of x. It's already irreducible. And so the next case will be f of x is not irreducible. But notice that that means that we can write f of x as g of x times h of x with the degree of g of x and the degree of h of x is between 1 and k. That's because we need the degree of g of x plus the degree of h of x to be k plus 1. But now what we can do is apply our induction hypothesis. So let's just get that here. We're applying our induction hypothesis to g of x and h of x. So that means we can write g of x as perhaps p1 of x all the way up to pm of x. And we can write h of x as q1 of x all the way up to qn of x, where the pi and the qj, so pi of x and the qj of x, are both irreducible polynomials. I really should say they're families of irreducible polynomials. But now we can just smash this stuff back together, and we have f of x is equal to p1 of x all the way up to pm of x times q1 of x all the way up to qn of x, and we have just written f of x as the product of irreducible polynomials. Okay, so that's what we needed for this theorem. Okay, so now we've got factorization into irreducibles. Now let's work to proving that this factorization is unique. Of course, if we're trying to draw some parallels between f adjoint x and the integers, well, then that means that primes and irreducibles should be the same inside of f adjoint x, because inside of the integers, there's no difference between prime elements and irreducible elements. And so that's what we're going to prove here. So in particular, we're going to prove that f of x in f adjoint x is irreducible if and only if it's prime. So now I'd like to observe this reverse direction is always true. A prime element is always an irreducible element. So in fact, there's nothing to do in that direction. So that means we should probably look at this forward direction. And if you don't remember the definition of a prime element, well, you can gain that definition either by looking at previous videos, or perhaps you'll see it show up in this proof here. Okay, so let's suppose that f of x is irreducible and that f of x divides the product g of x times h of x. And now, in order to show that it's prime, we need to show that f of x divides g of x, or that f of x divides h of x. That's the definition of primeness. If a prime, or if something that we want to call prime, divides a product of two things, it has to divide one or the other. Now we're going to use the fact that we've got polynomial GCDs when we're working over a field. So let's go ahead and let d of x be equal to the GCD of f of x and g of x. But now let's observe the following. That's going to tell us that we can write f of x as a of x times d of x, and we can write g of x as b of x times d of x. And this is where a of x and b of x are both polynomials with coefficients from our field. That's just the definition, or that's the common divisor part of the greatest common divisor. Okay, good. Now we're going to start breaking this into cases. So here's my first case. And that will be that d of x is not equal to 1. And then my second case will be d of x is equal to 1. But let's recall that greatest common divisors were always monic polynomials. So if d of x is not equal to 1, and it has to be a monic polynomial, that tells us that the degree of d of x is bigger than 0. But that tells us that the degree of d of x is equal to the degree of f of x. Because if you're factoring f of x into parts, given that f of x is irreducible, and you factor it with one part which is degree bigger than 0, then that means that has to be all of it. Okay, but now if these two have the same degree, then that means that the degree of a of x is equal to 0, but that means that a of x is equal to alpha in f. And I'm just going to put here it's a unit, because we're assuming that none of these things is 0. I guess I didn't carefully say that, but I think that's kind of understood here. Okay, nice. But now let's observe the following. That means we can write d of x as alpha inverse times f of x. This greatest common divisor is actually just a constant multiple of f of x. In other words, it's an associate of f of x. Now let's also note that means that we can write g of x as alpha inverse times f of x times b of x. Simply just replacing that d of x with alpha inverse times f of x. But observe here, that tells us that f of x divides g of x. And that's the end of this case. So if d of x is not equal to 1, then f of x divides g of x. Okay, so now let's move on to our second case, so case 2. and that will be that d of x is equal to 1. And that, of course, covers all possibilities. It's either equal to 1 or it's not equal to 1. Okay, so if it's equal to 1, that means that there exists polynomials, let's see, u of x and v of x in f of x with, let's see how we can write this, f of x times u of x plus g of x times v of x equals 1. That's because over a polynomial ring, you can always write a GCD as a linear combination of the two polynomials. That's one of the likenesses with the integers. Okay, good. Now what I want to do is take this right here and multiply it by h of x. So let's see what that leaves us with. We'll have f of x times h of x times u of x plus g of x times h of x times v of x equals h of x. So again, we just multiplied that equation by h of x. And then also, we know that we can write g of x times h of x as f of x times t of x for some polynomial t of x. That's because f divides g times h. But now what I'll do is simply take this g times h, and I'm going to rewrite it as f of x times t of x. But then I can write h of x as f of x times h of x u of x plus t of x times v of x. Just kind of reversing the order of this equation and then factoring an f of x out after making that substitution. But now let's observe that means that f of x divides h of x, which is where we want it to end for this thing to be a prime element. Okay, great. So now we've shown that irreducible is the same as prime. Now we'll show that we get unique factorization inside of this polynomial ring over a field. So we just finished showing that every polynomial can be factored into irreducible polynomials. Now we'll show that that factorization is unique. And so that would really be this parallel of the fundamental theorem of arithmetic. And we can package all of that together into one statement, and that is f of x is a UFD, a unique factorization domain. Okay, so let's suppose that f of x is p1 of x up to pm of x, so that's a product, and q1 of x up to qn of x, where those pi's and qj's are irreducible polynomials. And let's also suppose that m is less than or equal to n. So we've got that two different factorizations into irreducible polynomials, and we just take one of them and say that that's the shorter of the two. There has to be one that is shorter of the two, or they're both equal in length. Of course, we want to show they're both equal in length and that the polynomials are associates. That would prove that we've got a UFD, but that's kind of jumping the gun there. So let's say we're going to do induction on m, which is this smaller possible product. Okay, so it's induction on m, which means we need a base case. The base case here is quite simple. That's going to be the case when m is equal to 1. But that tells us that we have f of x is equal to p1 of x, but then it's also equal to q1 of x all the way up to qn of x. But notice that if p1 of x is irreducible, then that means that this product right here has to collapse to just one thing. Because, well, notice that we're factoring that into a product of irreducibles. But if you factor an irreducible at all of the terms except for one have to be a constant. But irreducibles are non-constants. That means that, well, none of those can be constants, which means it's going to collapse all the way down to just one thing. So we've got this is equal to q1 of x. So anyway, that proves that m is equal to n in this case, and that the lists are associates of each other. Anyway, there's not really a ton to do in this base case. Now let's move on to the induction step, which of course starts with the induction hypothesis. So the induction hypothesis here will be, suppose that this statement holds for all m between 1 and k. So here we're making a strong induction hypothesis, although I don't think we need a strong induction hypothesis. We need just a normal induction hypothesis, but this won't hurt. Okay, so, and to build off of this induction hypothesis, let's suppose we've got f of x is equal to p1 of x multiplied up to pk of x times pk plus 1 of x. And then that's equal to q1 of x multiplied up to qn x. Okay, cool. But now let's note the following, and that is that pk plus 1 of x divides f of x, but that means that pk plus 1 of x divides this product q1 of x all the way up to qn of x. And now, using an extended version of the result that we just saw with these being primes, that means that this pk plus 1 has to divide one of those. So remember, something's prime if when it divides a product, it has to divide one term from the product. And so that was done with a product of two things, but you can actually extend that to a product with more than two things. It's actually fairly straightforward, so we're going to leave that off here. So anyway, what that tells us is that there exists a j, which is between 1 and n, with pk plus 1 of x divides qjx. Okay, nice. But now we're going to do a simplification step, and that simplification step is to reorder so that we have a pk plus 1 of x actually divides qnx. Okay, good. But let's see. That means that we've got q sub n of x is equal to pk plus 1 of x times something a of x. But the fact that we've got a factorization of an irreducible, qn of x is an irreducible, we've got a factorization, and we know the pk plus 1 is non-constant. That means that we know that this a of x is constant. But that means that we can write this as alpha times pk plus 1 of x, where alpha is an element just from the field. But now what I'm going to do is take my original equation up here and rewrite it a little bit. So we've got alpha times pk plus 1 of x, and then times the product p1 of x all the way up to pk of x is equal to qn of x multiplied into the product q1 of x all the way up to qn minus 1 of x. So I just reordered some things there a little bit. And then I just realized that I shouldn't have put the alpha over here. I should have replaced this qn with alpha times pk plus 1 of x. But now what I can do is simply divide both sides of this equation by pk plus 1 of x. And then we've got this. But now we can apply the induction hypothesis to do two things. First off, we can say that k is equal to n minus 1. In other words, we've got the same number of irreducibles on both sides. And then we can also reorder so that the pi of x and qi of x are associates. But notice that qk plus 1 of x and pk plus 1 of x are already associates, keeping in mind that n is equal to k plus 1 by this equation right here. But then that means that our original factorization into two different looking things is actually the same, up to associates of each of these irreducibles. But if you look at the definition for a unique factorization domain, a UFD, that means we have satisfied the conditions for f adjoin x to be a UFD. So now I think we finished this first goal, which was showing that f adjoin x has a unique factorization theorem similar to the fundamental theorem of arithmetic. Now we want to look at the second goal of this video. So the second goal of this video will be to answer or give an incomplete answer to when is f of x a polynomial over the rational numbers irreducible. So we're not going to always know when it's irreducible, but we will be able to give some tests for determining when families of these polynomials are irreducible. So this is going to require a couple of lemmas. So let's start with this lemma. So let's say that f of x is in q adjoin x. then there exist integers rs and then a0, a1 up to an, where the GCD of r with s is equal to the GCD of all of the a's, which is 1, such that f of x is equal to r over s times a sub n x to the n plus all the way down to a0. Okay, so let's get to this. This is really just kind of a calculation type lemma. So let's write f of x as bn over cn times x to the n plus all the way down to b0 over c0. So we're able to do this because we know that all the coefficients are rational numbers. So we're just exhibiting them as rational numbers. Now what we're going to do is factor out all the denominators. So this is going to be 1 over c0 multiplied up to cn. And then we'll have dn x to the n added all the way down to d0. And this is where these di's are really whatever integer it takes to factor this out. I think we could write down a formula for these if we wanted to. Like for instance, di would be equal to bi times c0 up to cn over ci. So we've divided out that ci part. But that, again, that's just a calculation. So now what we'll do is set d equal to the GCD of d0 up to dn, and then we'll write di as ai times d, where the GCD of all of these ai's is 1. So if you take a list of numbers and you factor out the GCD, then what's left over is relatively prime, kind of necessarily. Okay, but now let's write f of x as the following. So we'll have d over c0 up to cn, and then we'll have a sub n x to the n added all the way down to a sub 0. But notice that these a's satisfy the condition that we're going for, and then we'll take this d over this product c0 up to cn and write it as r over s. Notice d times this product is simply a rational number, and we can write this rational number in lowest terms. But being in lowest terms is equivalent to the numerator and the denominator being relatively prime. So that finishes off this GCD rs being equal to 1. Okay, so there's our first lemma. Now let's move on to our second. Our next lemma is called Gauss's lemma, and it essentially says that if you've got a polynomial with integer coefficients that is factorable over the rational numbers, then it's similarly factorable over the integers. So let's look at it more carefully. So let's say we've got f of x in z adjoint x, and it's monic, so the leading coefficient is 1. So that f of x is alpha of x times beta of x, and those alpha and beta are polynomials with rational coefficients. So that's our setup. Then there are monic polynomials a of x and b of x satisfying some conditions. The degree of alpha is the same thing as the degree of a. The degree of beta is the same thing as the degree of b. And f of x is equal to a of x times b of x. So it's like we take this rational factorization and we build it into an integer factorization. Okay, so let's see how we might do this. So we'll start by using the previous lemma to rewrite alpha of x and beta of x in that nice form described in the previous lemma. So we've got alpha of x is r1 over s1, and then a sub m x to the m added all the way down to a sub 0. And then we've got beta of x is equal to r2 over s2. And then we've got b sub n x to the n added all the way down to b0. And then I'll leave off the GCD considerations, but we'll use those GCD considerations when we get to them. So now let's observe the following. And actually, before we do that, I'm going to take this a sub m x to the m all the way down to a0, and I'm going to write this as alpha sub 1 of x, just to shorten it. And then I'm going to do something similar here. I'll take this, and I'll write it as beta sub 1 of x. Okay, nice. And so now let's note that we can write f of x as r1 times r2 over s1 times s2 times alpha 1x times beta 1x. So just keeping in mind that f of x is alpha of x times beta of x. But now I'm going to push these two together into r over s, and then we've got alpha 1 of x times beta 1 of x with GCD of r and s equal 1. I just write that product of r1 over r, or r1 times r2 over s1 times s2 in lowest term. So that's something you can always do. But now let's observe the following. We have s times f of x is equal to r times alpha 1x times alpha 2x, or sorry, times beta 1x. But now I'd like to maybe multiply out this right-hand side and observe that it looks like r times am times bn times x to the m plus n plus lower order terms. Doesn't really matter with those lower order terms at the moment. Now we know f of x is monic. That means the leading coefficient in f of x is 1. But after multiplying it by s, that means the leading coefficient in f of x times s is s. But taking out the leading coefficients, that means that s is equal to r times a sub n times b sub n. Now I'm going to break this into a couple of cases. So if s equals plus minus 1, then that means that r equals minus plus 1, and then am and bn are also both plus minus 1. But then putting all that together, that tells you that f of x can be written as plus minus alpha 1 of x times plus minus beta 1 of x. Where I'm not being super careful about the sign here, the important thing here is if s is plus minus 1, then we kind of already have a factorization as long as we fix the sign. And this stuff over here is what it takes to fix the sign. Okay, so it turns out to be a little bit trickier if s is not equal to plus minus 1. So let's look at that on a clean board. All right, so let's recall that we wrote s times f of x as r, a, m, b, n, x to the m plus n plus lower order terms. And from extracting coefficients, we found that s was equal to r times a sub m times b sub n. Now, in the case that s was plus minus 1, we're done, so we're not going to talk about that anymore. So that means we need to look at the case when s is not plus or minus 1. Now, let's note the following. So since the GCD of an r and s is equal to 1, that tells us there exists a prime number p such that p divides s, but p does not divide r. So let's just talk our way through that. Since s is not plus or minus 1, then that means that it has a prime divisor. But then out of all of those prime divisors, well, we know that we can take one that does not divide r because the GCD here is 1. Well, actually, it tells us that all of the prime divisors don't divide r, but we're only guaranteed to have one prime divisor. Okay, and now we're going to take the equation which was the parent of this top equation here and reduce it mod p. So here I'll just put a squiggly arrow to mean we're reducing mod p, and then let's recall that that parent equation, if you will, was r times alpha 1s times beta 1s was equal to s times f of x, but that's equal to 0 in zp adjoin x. Because s is a multiple of p. We're reducing it mod p. Okay, nice. But notice we've got r, alpha 1, beta 1 is 0 in zp. r is not 0, which means that we know that alpha 1 times beta 1 of x is 0 in zp adjoin x. Right? Because this is non-zero, but then since we're in integral domain, that means that this part has to be 0. But now, since this is an integral domain, that tells us that one of these is 0. So 1 is 0 inside of zp adjoin x. Again, because we're in an integral domain, zp adjoin x is an integral domain. So let's say without loss of generality, alpha 1 of x is equal to 0 in zp adjoin x. But now, why is that a problem? Well, recall that alpha 1 of x was equal to amx to the n plus all the way down to a0. But the fact that this is 0 and zp adjoin x, that tells us that p divides a sub j for all j between 0 and m. But that means that the GCD of a0 up to am is a multiple of p. So is bigger than or equal to p, I should say. But recall that that GCD was supposed to be equal to 1, which means it can't be bigger than or equal to p. But that's our contradiction. Contradicting this ability for s to not be plus or minus 1, which means it is plus or minus 1, in which case we were already done. So now let's look at a quick corollary of that before we present a really classic tester for when something is irreducible in Q adjoin X. Okay, so let's look at our corollary to Gauss's lemma. So let's suppose we've got a monic polynomial f of x in z adjoin x, so it has integer coefficients. Then if f of x has a rational root, then it has an integer root. And furthermore, that integer root divides the constant term of our polynomial. Okay, so let's see how this proof goes. So let's suppose that we can write f of x as x to the n plus an minus 1 times x to the n minus 1 all the way down to a0. And then note that we have a root or a rational number a in Q such that f of a is equal to 0. But then that means that we can write f of x as x minus a times g of x. So if you've got a root of a polynomial, you can always write it like that. But notice that a is an element of the rational numbers. But what we can do is apply Gauss's lemma to take this monic polynomial which has a rational constant term and rewrite it as a monic polynomial with an integer constant term. So that means that there exists something that I'll call alpha in z such that f of x is equal to x minus alpha times, well, whatever polynomial makes this work. I'm going to write it as x to the n minus 1 plus a bunch of terms in the middle plus a0 over alpha. Of course, we know the top term has to be 1 because f of x is monic, and we know the bottom term has to be a naught over alpha because we've got this alpha right here. Now the important thing, and the thing that we get out of Gauss's lemma, is the fact that this right here is a polynomial with integer coefficients. But that tells us immediately that a naught over alpha is an integer. But that's equivalent to saying that alpha divides a naught. But a naught is clearly equal to f evaluated at 0. So that finishes off this corollary. Okay, one last result for the day, and that will look at this second goal a little bit more carefully. All right, so our last result will be something called Eisenstein's criterion. So let's suppose we've got a prime p, and we have a polynomial with integer coefficients where I've written it as an x to the n plus an minus 1 x to the n minus 1 all the way down to a naught. Then our assumption here is that p divides a sub I, where I is between 0 and n minus 1. But then p does not divide an, and then p squared does not divide a0. And if you've got all of those things satisfied, that means that f of x is irreducible over q. But let's observe by Gauss's lemma, we just have to prove that it's irreducible over z, and then again by Gauss's lemma, in fact it's the contrapositive of Gauss's lemma, we'll know that it's irreducible over q. Because if we've got a factorization over q, we've got 1 over z, which means if we don't have 1 over z, we don't have 1 over q. Okay, so anyway, let's see how this might go. So let's suppose that we can write f of x as follows. So it's going to be b sub k x to the k all the way down to b sub 0. And then it's going to be c sub l x to the l all the way down to c sub 0. So there we go. It's a factorization into smaller things. But now I'm going to multiply this out a little bit. So we're going to have bk times cl times x to the k plus l added all the way down to, and I'm going to write a middle term here, And this middle term will be B0Cm plus B1Cm minus 1 all the way down to BMC0, and then that's x to the m. And then this is going to go all the way down to B0 times C0. And I'd like to quickly observe that this thing right here is A sub m. But it's only A sub m if we have m less than or equal to L, because we've got kind of enough C's to go up to the right place, if you will. All right, so now let's jump right into it. So we know that P divides A0, but that tells us that P divides B0 times C0. Just by multiplication, we know that this term right here is the same thing as A0. And just kind of by the way, this term right here is the same thing as A sub n. But if a prime divides a product, that means that P divides B0 or P divides C0. Now, without loss of generality, let's say that P divides C0. Okay, but now let's observe the following. P does not divide BK times CL. That's because P does not divide A sub n. But if P does not divide this product, that means P does not divide B sub K, and P does not divide C sub L. So I think that's pretty clear. So that means that there exists at least one C that's not divisible by P. Now what we're going to do is let M be the minimal such that P does not divide C sub m. So we needed this argument right here just to show that there was one of these C's not divisible by P, and now we'll just take the smallest among all of those. And now here's for the final calculation. So let's notice that we can write A sub m as B0Cm plus B1Cm minus 1 all the way down to BMC0. And I'd like to observe that this part right here is divisible by P. You might say, well, what if that's A sub n? But we kind of know that it's not A sub n because this m is smaller than or equal to the degree of these C's right here. And I guess we're assuming that this is factoring into non-constant polynomials. Okay, so this part right here is divisible by P. And then all of this tail right here is also divisible by P. But let's observe that that implies that B0Cm is divisible by P. Because if those two parts are divisible by P, the leftover part is also divisible by P. Now we know that P does not divide Cm, but since it divides this product, that means that P does divide B0. But let's look at the problem that's just occurred. We have P divides C0, P divides B0, but that tells us that P squared divides B0 times C0. In other words, P squared divides A0, but that's our contradiction. Contradicting this ability right here to perform this factorization in the first place. Okay, so let's look at an example of this being applied, and then I'll leave you with some exercises. So here's an example of Eisenstein's criterion in action. So look at the polynomial 25x to the fourth plus 27x cubed plus 6x squared plus 9x plus 15. Now let's take our prime to be 3. Notice that 3 does not divide 25, the leading coefficient, but 3 does divide every other coefficient, but then 3 squared does not divide the last coefficient. So then by Eisenstein's criterion, this one is irreducible. Now for some exercises. Let's show that if n is composite, then Zn adjoint x is not a UFD. Let's observe by our big result today, we know that Zp adjoint x is a UFD. Now, the next one is to determine which of these polynomials are irreducible over Q. So I'll let you look at the polynomials. Some of them you can show are irreducible using Eisenstein's criterion. If you can't use Eisenstein's criterion, then you have to try to factor it. Now that's kind of a bummer, but notice that if you've got a fourth degree polynomial, either as a linear times a cubic or two quadratics. And then if you've got a fifth degree polynomial like this right here, well, you've got a couple of more possibilities, but it shouldn't be too bad. Now, finally, prove the rational root theorem. So in fact, the corollary that we had to Gauss's lemma was in the direction of the proof that you'll want to use for the rational root theorem. If you don't recall what the rational root theorem is, then feel free to look it up. And that's a good place to stop.